Okay, let's look at a power function. So a power function, the basic idea is it's f of x equals x to the p, like that. So we add our slider. Now, of course, we can, whatever we have here, we can move side to side, or we could scale it up and down, but essentially it's x to the p, and it's looking at what matters with p. And so I'm going to change this just a little bit to go from -1 to 2. So we'll try that. So here, when we're at p equals 1, we just have y equal x, right? So it just does that. Now, if we start to increase it, we should probably bring this down here. Notice that if we're at something like 1.06, it only goes from 0 out because, well, the 1 is fine. I can do x to the 1. That's if x is a negative number. But what the heck is like -2 to the 0.06? We might not be able to compute that. And so, but at other numbers, 1.08, all of a sudden it does exist, and so, it may or may not be there on the left-hand side. So usually when we talk power functions, we really are just worrying about x greater than or equal to 0. But notice what happens as I move up this way, just looking at the right-hand side, you see it's starting to look more and more like a parabola, and by the time I get up close to 2, at 2 it definitely will be the parabola y equal x squared, but it's looking more and more like a parabola. So, and of course, if we went to cubed or to the 5th power or something like that, it's just steeper and steeper, but has this nice bend up. So that's between 1 and 1. Well, it's greater than 1, right? Anything greater than or equal, well, greater than 1, it will be bowed up like this. We will soon be calling this concave up. So, that's what we get whenever p is greater than 1. If p equals 1, we get the straight line. Now, what if we're below 1? Then we get something like this, and definitely it's not going to want to fill in the left-hand side very often. It can, so you see we get it there, but not too often because we're taking roots, right? So if I get down to the 0.5, wherever it is, 0.5, that's the square root function, right? That's x to the 1/2. So that's the square root function. And so when we get below 1, it ends up being what we call concave down. It still starts at 0, but it bows down. And it grows relatively slowly. And as I get closer and closer to 0, it does that more and more. Okay, and it's pretty steep here, and then has a pretty sharp curve. But it's the same basic shape. So if I were to have data that looked like that, I would think of something like x to a power less than 1 but greater than 0. And then when we get over here to negative, all of a sudden, well, a negative power, that means it's 1 over x to the 0.1, and we're not defined at x equals 0 here. So this is actually a vertical asymptote here, and it's not, the function's not defined there, and we get this basic shape like this. And again, depending on what it is, it may show up, and here it's showing up symmetrically like that, but it doesn't have to, they don't have to be both positive. They, the other one could be it could be an odd function sort of thing, and the symmetry through the 0 here, the 0, 0 origin. But again, on the positive side, we are always just seeing this same shape. It comes up really close to the y-axis, but grows very tall there, and then bends down and does a shape like that. And so if I see data that do this, that may be a function I want to go with. And even if that data has a y-intercept, well, that's no big deal. Again, all I have to do is move this thing to the left. So for instance, if I did f of x plus 1, right, then all of a sudden I have a y-intercept. The vertical asymptote problem is all of a sudden over here. So, the data don't have to look like they're growing greatly up there to decide to use a power function with a negative exponent, because all I have to do is shove it over a little bit to the left, and then, oh yeah, I've got a y-intercept right there. So that's negative exponents. So really just kind of those three things. The exponent is either negative, which gives you this kind of shape. It is positive between 0 and 1, which gives you this square root looking thing, or it's bigger than 1, in which case it's starting to look kind of like x squared or x to the fourth or something along those lines. Okay, so that's a power function. Exponential looks similar. It's just pieces are reverse here. So let me get rid of that. Now normally we would use a b to the x. Add a slider for b. And of course if x is 1, well, it's just 1 to the x. I just get the constant 1. Now if b is bigger than 1, what happens? Oh, well, it grows greatly as x is positive, and it diminishes here as x gets more and more negative. But b to the x, so you've got, let me make it like a 2 to take numbers that we get a little better, right? Is that if I take 2 to any power, it could never be a negative number. And so what happens is like 2 to the negative 10th, or well, here negative 4th, but 2 to the 10th is 1,000. So by the time I get to 2 to the negative 10th, that's 1 over 1,000. That's really tiny. It's basically 0. It's getting close to 0. But it can never be 0, because I'm just taking 2 and multiplying it some number of times, and then maybe 1 over, or not if I'm over here with x. But it's always got to be positive, and so it can get no smaller than 0. So I know it has a horizontal asymptote at 0, and that's as it moves out toward the left. As it goes to the right, it grows and gets really, really big. Now, what happens if, so that was b bigger than 1, and pretty much if I do that, see, it just keeps looking the same. Now, if I get in here between 0 and 1, then those are, well, let me take it to 0.5. That's like 1/2. And, well, 1/2 is just 1 over 2. And so, that's like 2 to the negative something. Well, so this is going to be just the symmetric curve about the y-axis. Whereas when b was 2, it grew really big over to the right. Well, now when b is 1/2, it's going to get big as it moves out to the left, because all of a sudden it's a negative number. I have 1/2 to a negative exponent. Well, that's the same as 2 to a positive exponent. And so when b is between 0 and 1, I get the same sort of behavior, but it's coming down from very large numbers as x was very negative. It's coming down, again crossing the x-axis. As long as I don't multiply by anything or shift it up or down or to the left or right, this thing is going to be going through 0, 1, because anything to the 0 power is 1 except 0, but we don't have a 0 here. We're staying greater than 0. So for b less than 1, it looks like this. B greater than 1, it switches to growing big this way and having the asymptote out to the left. Here, when I get, whoops, let's try that again. There we go. Between 0 and 1, the asymptote is out to the right, and it gets smaller and smaller and smaller. Yeah, if I try to make b negative, it disappears. It doesn't work well, right? Because I'm trying to take various powers of a negative number, and, well, depending on what x is, I can't do that, right? I can't take the square root of negative 3. I can take, I can take the cube root, but so even positive x, though, because you say, well, but you could do negative 3 cubed. Sure you can, but you can't do negative 3 to the 2.5, because there you're trying to take a square root of negative 3 as part of that, and so you can't do that. So negatives make no sense for b. Okay, so now another property about b, though, is let's look at some positive ones. Let's say b is 2. Now, notice, okay, here we're at 0, 1, and to get to 2, I guess to keep it there I have to hold it, but to get to 2 I had to travel 1. So to double, I traveled 1 unit this way, okay, and I was at 2. Now travel 1 unit again, and, well, if I can get it in the right place, I doubled again. Okay, but that is just the property of the fact that I'm taking powers of 2. But b then would be for each unit that I move to the right, how much is this going to grow in a multiplicative sense, right? So it doubles each time I move to the right. So remember, with a straight line, every time I move to the right, it increases by the same absolute amount, or decreases by the same absolute amount, right? If I move 1 to the right, if the slope is 5, if I move 1 to the right, it goes up 5. If I move another one to the right, it goes up 5. With exponential functions, what happens is, if I move 1 to the right, it goes up by a factor of b, right? Because, again, say b was 2, if I have 2 cubed, and then I do 2 to the 4th because I move over by 1 on x, well, what did I do? Well, I did 2 cubed times 2, 16 and 16. So you see, moving 1 to the right, that's adding 1 in the exponent. You're multiplying your previous answer by whatever b was. And so that's something you can think about with b. If you look at some data and it doubles, say, every unit, then, oh, well, then I'll use b equals 2, or I could use b equals 2. If it triples every unit, oh, well, I'll use b equals 3. If it seems to go up by 1.5 times with every unit to the right, oh, well, I'll try b equal 1/2. Okay, so that's a neat property of b. Now, that said, the way we're going to tend to look at exponential functions, instead of changing the base b, we're actually going to do it as f of x equals e to the bx, like that. And that b, so we're thinking of e to the x, and then we're using that multiple inside. We're kind of thinking of f of bx, right? We're putting that b there. Now, the reason for this is in calculus, life is just way easier when we're working with the base e instead of a general base b. Okay, so here our base, since this is equal to e to the b, and then I need to put that in parentheses, to the x, oops, somehow I missed getting that, to the x, then you see that the blue line and the green line are the same. Okay, so here this e to the b is our b here. It's our whole base. So yeah, that's kind of a pain. It can be a bit confusing. We aren't going to mess with that very often. I mean, pretty much when we look at exponential functions, we'll look at it this way, and so it just makes it a little bit rougher to talk about that nice property that we had back here with the unit change. You know, if I go 1 over to the x, because here as I change by 1 unit, well, it changes by e to the b, not b, and as far as a multiplier. Okay, so but we will do this, but the same basic things happen as far as the value of b, similar anyway, a little, you know, in that as long as we're greater than 1, hey, it's all the same, right? It's increasing. Now here's where it's a little different, because you see, if I'm using this e to the bx, well, if b is between 0 and 1, then it still is growing up here. Well, why? Well, because, let's get rid of this x here and look at the value of e to the b. Oh, I gotta go back one more. See, e to the b is bigger than 1, right? And that's the base. So when I have this b bigger than 0, my base here that I'm actually using is bigger than 1. And so these are slightly different in that they work basically the same, but the difference is here things change at 1, here they change at 0, and when b is negative, then you see my e to the b, the actual base I'm using for the exponential, is a number between 0 and 1. Okay, because at b equal negative 2, 1, that's 1 over e to the 2.1. That is a positive number, but it is less than 1. Okay, so a little bit different, but I think it is worth realizing that either of these is fine. It's just we're going to use this one, so if you really just want to concentrate on this family, the exponential family looking like this, where b can be any number between minus infinity and positive infinity, and just, you know, the sense of whether the function is decaying like this or growing like this, it changes at 0. And that is a convenient thing, right? Is negative, it's decaying; positive, it's growing. So you could choose to think of this family as this way. You don't really have to do it that way. But again, I believe in full information and realizing that, well, this is a nice notation or a nice way to think of the family. But again, in calculus, this tends to be the more convenient way. All right, so that was power functions and exponentials. I think we've done enough in this video, so we'll stop there.